but it's not great if you want to make something different. And that panel that you just saw came from a series of self-simmer panels, which are there are 488, and they're all different. So they start from being this long and this wide to being this wide and this long, and they're all formed of the same parameters that describe them. But we're not constrained by having any tooling to make them. So all of that information is not held in blocks of metal, it's held in the computer. So we're quite free with how we use that. So I guess as a sort of introduction to the process, you could first of all think about like what does sheet material want to do? And it doesn't want to be stretched with a mold, it just wants to, but it really wants to crumple up. I mean, that's its kind of natural state, is to fail. But if you look at that, you've got these beautiful little curves appearing in it. And I mean, I drew this one here by hand with a knife, but the other ones here are pretty similar in terms of their shapes. They look nice. So it's kind of a natural thing for sheet material to do. And that actually means that this process uses much less energy than normal sheet metal forming. So one of the grants we got from the Carbon Trust made some analysis, and we found that over kind of typical pressing run, there's sort of 60 to 80% energy saving. That translates to electricity and cost saving, so they're all kind of the same thing. So it's quite a major step in terms of efficiency there. And kind of, yeah, I think it's important to see maybe the similarities with something like 3D printing here is that this is driven by digital models. But we're also stepping one step back from that, and we're saying, well, don't start with a digital model. It's not really the best place to start if you want to be creative. Start with something that is paper, something that's a craft, hands-on approach, and then translate that into something digital, and then you can free that up. So once we get something that works in a paper model, we can then say, now start parametrizing that, so make it longer, wider, change the fold angle, etc., which is where the benefits of the robotics comes into it. And that was that kind of idea was born out in this project last year at the Venice Biennale, which was a large sculpture for Zaha Hadid architects. We worked directly with their design team in a workshop over 4 days, sort of exchanging ideas, us bringing our sort of domain knowledge of the sheet metal forming, the robotics, software, basically what was possible with this manufacturing process, and also giving them a lot of information about how they could build their own software to model this form, and so they could embed those manufacturing constraints within their own design process. And this was the 488 panels I described, which were all different. So we had to not only model each panel so that it could be sort of scaled and changed, but those panels had to drive the robotic production as well, so we had to make sure that we could fit that within the constraints of the robotic manufacturing process. But yeah, it all started with pieces of paper. So in a way, it's extremely accessible. Everyone can pick up a piece of paper and just fold it up, and then you can say, well, let's make that into something, let's scale it up. So all those sort of properties of the paper, this springiness, this curvature, do scale up really well, and they're pretty consistent. If you get a thicker piece of metal at a larger size, it's very similar properties. Okay, I'll show you the sort of things we've been making. Surfaces is one of them. So taking these shapes, replicating those. So we've had a lot of interest in this technology from the architecture profession. We've done lots of workshops for architecture schools. This was the ETH in Zurich. And basically we come in and we'll show people how to design with this process, and give them software tools, and then they'll extend those to use them for their own design. And they're very much I think these workshops are very much exploring what are the possibilities and the boundaries of this technology, because it is a young technology. Despite the fact I started it half a lifetime ago, it's not mature yet. We're still developing software, we're still developing processes, finding out what's possible, finding out what the market is, finding out who wants to use this process and what they want to make with it. And architects have been kind of a great audience for it in a way, because they've been promised in their software that they can make any shape they want for years now. And the software's becoming more and more sophisticated in saying you can make a building with 1 million different components and they're all different. And then you ask them to make it and they say, well, don't be stupid. Like, let's rationalize that down to 4 sets and let's build it. So that's really typical in that field. So we're saying, no, just make 1 million different components. They don't need to be the same. So that's quite interesting for them. It is constrained quite heavily as well, because there are material properties that have to be adhered to. So there's still that problem. You can't just design anything in CAD software and say, now go and make it. You have to actually consider how it's going to get built. But the software we've been making, which we'll have a look a bit later, we take those considerations, those constraints into consideration, so that you can't design something that's not makeable, basically. But I think the point about the sort of maturity of this technology in the context of tonight's topic is that, in fact, 3D printing is not mature either. There's a lot of hype, but in terms of how developed technology is, it's pretty similar to what you see here. We can make lots of really nice looking things, and you can do that with 3D printing as well. We can make some very useful things for specific audiences, which you can do with 3D printing as well, but it hasn't become accepted in the mainstream. It has in certain industries, like in architecture, product design, automotive, at some point maybe in the future, this is sort of accepted. So it's quite similar in that there are it's easy to see lots of promises of all the possibilities, but you have to still see the constraints of the process. I guess the difference is between this and 3D printing is this is maybe a bit more, requires a bit more investment, so it makes bigger lumps of metal, whereas 3D printing is kind of optimized for little small things like this sort of size. So there's a lower barrier to entry there. You don't have to spend tens of thousands of pounds on robots. You can spend thousands of pounds on a small machine. So, yeah, we don't know what 3D printing is good for yet, I think is what I'm trying to say. And same with this process. You can engage with these new technologies, but we shouldn't be too fooled by the hype, as Elliot pointed out, that these things they're here, but we don't know why yet. Okay, some more facades we've been designing with our software, we've been developing. I'll show you a bit more of that in a bit. So some of the products that we've been working on. Little table, which is actually still a prototype in card. So we can make, so this is 1:2 scale, so it's quite easy to prototype in sheet materials. There's a nice little bowl here, which is sort of looking at taking something that's crumpled in a really abstract form here and trying to rationalize that, make that repeatable. Looking at the light here, looks at other ways the material crumples, so actually forming that light without any set kind of way it should fold, just providing lots of options and seeing what happens. And a chair here, which is the output of one of the workshops we did at the Royal College of Arts with the Design Products department. This was someone who'd never designed a chair before and never folded bits of metal before, and pretty much on the first day had a chair design. And then they had a couple of weeks to kind of fold out metal and things, which didn't really change. So it's pretty, I think it's very accessible as a technology. Here, the following slides are sort of a few images of projects we've initiated. This is a sculpture at the D Hub in Barcelona, a shelf we designed. But again, to us this is one component. It just happens to vary in shape depending where it is to its neighbours, but it's still just one component. So all the information, all the development is based around one single component, and it can vary in shape. Some images, some more nice interior applications. So you can see that it's quite aesthetic. The sort of emphasis here is on it looks nice, really. And when I started looking at this technology, as I told you, looking at making a bike from it, my kind of way of evaluating this was, A, does it look good, and B, can I make it easily, and C, like, does it work structurally? So, and maybe D, like, can I afford to make these things? So there was kind of there's lots of things at play there, but if it doesn't look good, then you kind of have to discard the whole process, I think. It's no good having something that's practical to make and doesn't have tooling if it's extremely expensive and looks ugly, which there are lots of other attempts at removing tooling from sheet metal forming, but this wasn't really the intention with this process. It was, okay, it's quite risky to start making these forms that are not the same as the types of forms created with tooling. So we can't replicate car body panels using this process because there's not the same types of geometry. So that's quite risky, but we have massive upsides in that it looks really nice compared to your average car body panel, and we don't have any tooling. So it's quite unconventional in its sort of feature list, I think. This was some output, again, of some software we've been developing, which we'll have a look at. More ideas of how you could use the process. So, yeah, the process. So, it starts with paper. If you fold a piece of paper, we can then simulate that in Rhino and Grasshopper, which is some CAD software. We've written our own plugins to generate the CNC code for our router and our robot directly from the sort of model that you create. And also the animation of the model is simulated and used to drive the robots. So industrial robots are great, they're just like a human arm, they move. But typically you would say, go here, pick something up, go here, put it down again. And you teach a robot how to move through space by just recording points. So it's all relative to the environment. So what we developed was a system where you can actually program that in the computer where it's relative to itself and the data, which is like a table in our case. But we had to do that because you can't say, like, when you start folding this, there's such a complex sort of curve occurring, sort of path through space occurring that we can't record each one bit by bit and get it right, basically. So we do all that as a simulation of a folding and just take one of these points as it moves through space and say to the robot, just follow that, please. Which is nice and easy in the simulation, but in the real world we reverse that and say, if you move through this path, the material will have to follow that as long as we put it in the right place and store the piece of material as it is in the simulation, it will then form it. So
Does that work? Is that kind of deterministic, going from the stuff?
It works.
The software does it, and you give it to the robots.
Yeah.
The thing comes out the same as the thing you hope
Exactly.
it does.
Yeah.
That's amazing. It doesn't require a lot of your skilled knowledge to kind of.
It does require some. Yeah, we have to say like where should we put the robot?
Yeah.
There's quite a large surface there. We've got these 3 contact points currently with 2 robots and a fixed arm. So if we had more points, it would be easier. You could just say, just cover it in robots, and, but there's only enough room to fit a certain number of things. So it basically works. Yeah. One of the reasons it works is because we don't just give it a flat sheet and a line in our simulation. We actually describe. So this surface could exist like this, but it could also, I could twist that different ways. So for that same fold, I could have different number of configurations. If we assume this angle is staying the same in the middle here, like this could be quite different. So it will always, in our simulation, we try and take that information from its kind of resting state, the sort of equilibrium where it's in a format that it wants to be in. So the metal will have a similar end state. We could say fold it to like that, but it'll just go like that when we let go. So we don't bother trying to.
So you model the physical.
Yeah, we model those physical characteristics.
It's steel, so it's not just.
Yeah, exactly.
It's a dynamic model.
Yeah.
Yeah.
Well, I mean, a lot of the time we just take that directly from the paper model because it's so similar to the steel. Or if we want to be really accurate, we'll fold something in aluminium by hand and then analyse that surface and use that for the simulation, so we're as close as we can possibly be, which is quite an empirical way to do it, and it would be great, again, to embed all of that in software in good time. So this is people folding in a workshop. So it's very difficult to understand what's possible with these types of surfaces intuitively, because we are really clay modelers historically as humans. We see amorphous sort of blobby objects like people most of the time, and we understand those shapes intuitively. We can design, if we close our eyes, we can carve shapes in our head like relatively easily, I think. Maybe designers do more of it, maybe they can do it better, but it's very difficult to sort of fold shapes in your head when they're curved folds. So you have this convex surface adjacent to a concave surface, which is not intuitive. That's molded objects, like you see, like, I don't know if we've got any useful example molded objects, but like the corner of this knife or the cap on here, they have positive curvature in this direction and this direction that blends into each other. That's pretty normal for most things in our world, but it doesn't happen here, so you have to kind of get a feel for it. You have to start to follow the direction the material takes you rather than your ego takes you. So it's quite difficult for some designers to actually get into it because they want to say, I want this, but you can't just have this, you have to see what it gives you. So it's quite process-based design methodology. And as a result, some of the output is very unexpected. You don't get what you're expecting, you don't get what you want, but you get a lot of input from this into what directions you could go in. We do a bit of that with the robots. So this is us saying, I have 3 robots, can I form this shape? So rather than going through the whole process of simulating cutting metal, setting up the robots, we just say, well, just try it and get 3 contact points. So normally when you fold something, you sort of work your way along it slowly and get it folded, but that doesn't happen with the robots. You've got to be able to just take 3 points and just do the whole thing simultaneously. So it's quite quick to just test if that's possible too. And these sorts of things are small scale, they're really rough, there's no cost for making a mistake, and we kind of encourage making in this way at early stages, because you shouldn't be trying to make something perfect.